Hi, this is Jonathan Gardner, and this is homework help. This is problem number 155 of Schroeder's An Introduction to Thermal Physics. And this problem was one of the most fun I've had in a long time. I actually had to go all over the internet to look for help to solve different parts of this problem. It wasn't, just looking the tables in the back of the book and stuff like that. I imagine that if I was recently out of a introductory physics course, I could probably grab some equations from my previous textbook, or if I needed help, I can go ask, my teacher's assistant or the professor for, where do I go to look up these things, or how do I calculate these things. So problem A. So I'm going to do this problem I'm going to try to give you hints on how to solve the problem and then actually go through and solve the problem. So I encourage you to, once you kind of get an idea of what you want to do for this problem, I want you to pause this video or turn it off and then go into a corner by yourself and start trying to solve the problem on your own. So I'm going to give you some hints to move things along. So first problem. Problem A, consider a system of just two particles. So there's two particles. They each have identical masses. So we're going to say they have mass m. Okay? And then they are orbiting in circles about their center of mass. So they're orbiting in a circle about the center of mass. Okay, so center of mass, what does that mean? This is a basic concept from introductory physics. So if you have multiple objects, and so in this case we have two objects, one has a mass m and the other has a mass m, and then the center of mass is going to be in between those 2 points. So this is the center of mass, okay? So they are orbiting in a circular orbit, right? So they're making a circle about that center of mass. So we can label that distance here. This is the radius of the circle. We're going to call that r. And we want to show that the gravitational potential energy is minus twice times the total kinetic energy. So we need the gravitational potential, and then we need the kinetic energy, okay? So what I did for this problem, I'm not going to do this right now. I'll give you kind of some hints on how to go. If you have an idea on how to solve this problem, if your only hang-up was you didn't understand the problem, well, now you should understand the problem. There isn't much to question now. So the first thing that I did was I wrote down the vectors, the formulas for the vectors of the positions of the two particles. And then I wrote down the velocities of the two particles, and then I wrote down the accelerations of the two particles. The next thing that I did was I related the angular velocity of the two particles with the big G, right? So I calculated the force is equal to the mass times the acceleration, and so I was able to get the gravitational force equal to something with the omega on the other side. So the gravitational force, if you don't remember, the force due to gravity is equal to minus g times the two masses divided by the radius squared, and it's pointing in the direction of, let's just do r hat, right? So if r is a vector pointing from one object to the other, the force due to gravity is pointing in the opposite direction with this magnitude, okay? So that is able to give me a relationship between omega, or actually omega squared. I'm using omega for how fast the thing rotates when I wrote down the equations of position. And so I'm able to relate omega with the big G and with the R, okay? Calculating the potential energy wasn't too difficult. I had to go back to first principles because I forgot the formula for the potential energy of an R squared field. And so what I did was I actually calculated two potential energies. So I said, how much energy does it take to take one particle all by itself and move it into position? The answer is it doesn't take any potential energy at all. It's only when you have two particles interacting together. And so what I did is I had an integral where I started at infinity, and then I brought this particle up to 2r away from the particle because these particles are separated by a distance of 2r away. And then inside of here, I had the force vector, dot dr vector, okay? And this will tell you the potential energy, okay? Now note that when you're bringing the particle closer and closer and closer, which is what we're doing here, we're bringing the particle closer and closer and closer, the force and this guy point in the same direction, Okay, so there's a little bit of a twist there. Okay. At this point, let's see, you may also need to remember that the kinetic energy is just 1/2 the mass times the velocity squared. So if you're able to write down the vectors for the position, the velocity and acceleration, you should be able to solve it at this point as long as you're careful with all of your signs. So at this point, if you want to go and solve this, which I highly encourage you to do so, you should stop the video and shouldn't watch anymore. Okay, now I'm going to show you my solution. If you copy this solution and give it to your professor, you're a bad person. You should feel bad, okay? All right, so first thing I said was we have the position of one of these particles. It's going to be at a distance r. I'm using 0, 0 as a center of mass. And I'm going to say this has cosine omega t and sine of omega t for its x and y coordinates, okay? Why did I choose omega? I just needed a number. Okay, so I just chose omega because it seems cool, okay? The velocity of that particle is the derivative of this, which is going to be r omega minus sine omega t, cosine of omega t. And then the acceleration of this particle is going to be r omega squared. This is going to be minus cosine omega t and minus sine omega t. And we'll note that the x2 position is always equal to the minus of the x1 position, and so the velocity of this particle is also opposite the other velocity, and the acceleration of this particle is opposite the acceleration of the other particle. So there's no surprises there. All right, so now I'm going to equate this force with omegas by saying F vector equals m a vector. So we have g minus g. Well, we'll figure that out in a second. The two masses are the same, so that's mass squared divided by r squared has to equal the mass times the acceleration. So mr omega squared. And the acceleration is going to be in the same direction as the force, so these are going to be the same sign. Okay. And that's basically the equation you get there. Okay, so moving some terms around, we can say that omega squared is equal to, what did I get? Yeah, there we go, gm over 4, why did I get 4r squared? Gm over 4r squared. Oh, the force is 4r squared because the distance between the two particles is 2r. So the force is 4r squared. And then we get gm over 4r cubed. Okay, so this is a pretty key part of this problem, right? Mapping the orbital velocity of these particles to the force, big G, okay? Let's calculate the potential energy due to gravity. So that is going to be the integral from infinity to 2r of the force vector dot the dr vector. Okay, so we're going to start way out in infinity. We're going to move up to 2r. The force is always pointing the same direction as motion. So this is the integral from infinity to 2r of g m squared over r squared dr. All right. The integral of this is minus g m squared over r, evaluated between infinity and 2r. So that's just minus g m squared over 2r. And that's the total potential energy of the system. Okay. It's just the energy it takes to move one particle within 2r of the other particle. Okay. Notice the minus sign. So as you get closer, as you get closer and closer, there's less and less potential energy. Okay. All right. So let's calculate the kinetic energy. This is just 1/2 mv squared plus 1/2 mv squared because there's two particles. And the velocity squared is going to be r squared omega squared. Okay. So we get mr squared omega squared. And if we recall, the omega squared is gm over 4r thirds, 4r to the 3. So we have mr squared gm all over 4r cubed. So that's gm squared over 4r. Okay, so that's the total kinetic energy. Okay, so we note that the kinetic energy is equal to minus twice the potential energy because of these two formulas. I have a graph here to show what these look like. Okay, so at the radius 1, right, we have the kinetic energy is 1/4 gm squared over r, And the potential energy is 1/2 GM squared over R. And so the total energy is down here. And you can see how as you increase the radius between the two objects motioning in circular orbital motion, that the energy, the total energy, starts to increase towards zero, right? The kinetic energy drops towards zero, but the total energy increases towards zero. The potential energy obviously is twice the size of the kinetic energy, but minus. Okay, so that's a very interesting result for this system. All right, moving right along, let's do part B. Part B says the conclusion of part A turns out to be true, at least on average, for any system of particles held together by mutual gravitational attraction. So we have the average potential energy is equal to minus twice the average kinetic energy. And this is Virial's theorem. What would happen if you were to add some energy to such a system and then wait for the system to equilibrate? I don't know what the right way to pronounce that word is. Does the average total kinetic energy increase or decrease? Explain. So we have the total potential. So we have the average total, which is just going to be the average of the potential plus the average of the kinetic, which is equal to minus 2 the average of the kinetic plus the average of the kinetic, which is just minus the average kinetic energy. So if we were to increase the total energy, then the kinetic energy would decrease. Okay, going back to our graph for the circular motion, you can see that as the total energy, this green line, increases, the kinetic energy is decreasing. Okay, that's what's going on there. Problem C. C is a little bit strange. Okay, so a star can be modeled as a gas of particles that interact with each other only gravitationally. According to the equipartition theorem, the average kinetic energy of the particles in such a star should be 3/2 kT. So 3/2 kT should be the average kinetic energy of each particle, not the entire system. Up until now, the kinetic energy we've been talking about was the entire system. Okay. Express the total energy of a star in terms of the average temperature and calculate the heat capacity. Note the sign. Okay, so we're going to have to calculate the total kinetic energy. The total kinetic energy is going to equal the number of particles times the kinetic energy for each particle, which is just going to be N times 3/2 kT. Okay, so we want to express the temperature as T is the average temperature. Express the total energy of a star in terms of its average temperature. So the total energy of a star is equal to minus the kinetic energy. Okay, so we're going to say that this is equal to minus the total energy. Okay, so T is equal to minus the total energy. That's a time sign there. It's not a minus sign. And then we have 2/3. And then we have KT. So we can just put U total. So minus 2 U total all over 3K. I'm sorry, there's no T there. This is the K. Okay. So we have the number of particles as well. NK. Okay. So this is the average temperature. It's minus the total energy, 2/3 of total energy divided by the number of particles divided by Boltzmann's constant. What is the heat capacity? So the heat capacity is defined as the heat over the change in temperature. So we can break that up to the change in the total energy of the system, the total internal energy divided by the temperature, and we can subtract out the work over the change in temperature. We're just going to ignore the work term for now. So we have, if we take du by dt, so we take this equation, This is the total. And we take the the temperature derivative. That's going to be minus 3/2 Kn. Okay. So that is how that's the potential. This is the heat capacity. That's roughly the heat capacity. Okay. Minus 3/2 Kn. So as you add more heat, the energy drops. Okay. And that's what this sign means. So that minus sign is pretty important. Again, the reason why this does this is because as the energy increases, the kinetic energy decreases, right? And the kinetic energy is tied to the temperature. All right. So we're going to see as you increase the temperature, as you increase the heat, the temperature is going to fall. Adding heat, wait, hold on, one more time. Adding heat will cause the temperature to fall. Yes. Yeah, that's true. Adding heat will cause the temperature to fall. Okay. Problem D, or part D. This one is to use dimensional analysis. So we're just going to look at the dimensions. So we are going to use dimensional analysis to argue that a star of mass m and radius r should have a total potential energy. So U potential should be equal to minus Gm m cubed, m squared over r times some unitless constant. Okay. So this should be Newton meters or joules. Okay. So we're going to see that G, so we have, well, forget the minus sign, that doesn't matter. The G is force, so it's newtons. And we have to divide, we're going to divide by distance squared, so meters squared, divide by kilograms squared, okay? Because the force due to gravity is equal to G m squared over, or m1, m2 over the distance squared, right? So G is in units of force, r squared divided by m squared, okay? And then we have the mass squared, so that's kilograms squared, divided by the distance, so that's meters, and that dimensionless constant doesn't have any dimensions, so this is Newton meters, the kilograms cancel, the meters cancel, and so this is a joule, okay? So the potential energy with this formula gives you the joule. That's all it's asking for. It's not very complicated. Problem E of problem 155. This is a fairly involved problem. It took a while for me to solve this one. I did have to go to the internet to calculate some things, but let's look at the problem definition first. It says estimate the average temperature of the sun whose mass is 2 times 10 to the 30 kilograms and whose radius is 7 times 10 to the 8th meters, okay? And he says, assume for simplicity that the sun is made entirely of protons and electrons. All right. So understanding this problem, we need a formula that will relate the temperature of the sun to the number of particles, its mass, its radius. Okay. And if you've been doing the previous problems, you should already know what that formula is. The formula for the temperature would be minus 2/3 the total potential energy divided by Boltzmann's constant K and the number of particles. So that's the formula that we need to use. The strategy for this problem is pretty straightforward. We need to calculate U and we need to calculate N. Okay, so N could be done if we know the mass of the protons and electrons, we know the total mass of the sun. There should be some relationship between the number of protons and electrons. The potential energy is much more complex, so we'll probably tackle that first. If you wanted to solve the potential energy on your own, let me give you a strategy to do so. So in order to solve the potential energy on your own, take the sun, radius r, and then take shells, radius little r, apart. Assume that there is an average density and that it's constant, so that's just the total mass of the sun divided by the volume of the sun, and then calculate the potential energy due to each slice. Okay, that's going to be minus G times the mass of the sun on the inside of that radius, so the mass up to that radius, times the little slice of shell that you're bringing in over the radius that shell is being brought into. Okay, so this should be enough to calculate the total potential energy of the sun just on a gravitational basis. All right. Going to solve this problem altogether. So let's go ahead and do what I recommended you do. And so we're going to get du is equal to minus g times the total mass of the sun on the inside. So the density of the sun is given as 3/4 the mass of the sun divided by pi r cubed. Okay, this is just the mass of the sun divided by 4/3 pi r cubed, which is the volume of a sphere of radius r. Okay, so we get 3/4. The 3/4 the mass of the sun divided by pi r cubed times the volume of the stuff inside. That's 4/3 pi r cubed. Okay, so that's the mass on the inside of that shell. And now we need the mass of the slice. So that is I'm just going to write this on the second line over here. So times the mass of the slice. So we're going to go, we take the volume of the shell, which is 4 pi r squared dr, times the density, 3/4 the mass of the sun divided by pi r cubed. Okay, and then all of that is divided by the radius r. So if we take the integral from 0 to r of the potential energy of each of those slices, right, we are going to get minus g at the top. 3/4 cancels 4/3. We have an m over there, so m squared. Pi cancels here. Pi cancels here. This 4 cancels there. We have a 3 left over. So we have r to the 5th divided by r to the 6th. We actually have an extra r there, so it's r to the 4th. Okay, so that's the integral of that times dr. We're going from 0 to r. And so the integral of this is minus 3/5 of g m squared r to the 5th all over r to the 6th. So that's minus 3/5 g m squared over r. Okay, that is the potential energy. All right, now we need the number of particles. In order to do that, we notice that the number of protons must equal the number of electrons because the sun does not have a net charge. The mass of a proton is much more massive than the mass of an electron. So we are going to use, the mass is 1.67 times 10 to the minus 27 kilograms. Okay, we divide the total mass by this, and we get the number of protons is equal to 3.346 times 10 to the 57. And so the total number of particles is 7 times 10 to the 57. So that's the total number of particles. This is the number of protons, which is equal to the number of electrons. Okay, so it's twice that. And when we take 2/3 of that times that, divided by Boltzmann's constant, and divided by the number of particles, we get the temperature is equal to 700,000. Okay, this is a very interesting problem. It's really cool. It's really interesting to do. Anyway, guys, have a great day. Take care. Find me on Discord if you have any questions. Bye-bye.